Welcome back students for the second video lecturing on electrical conductivity of metals. In this video we will discuss about the failures of classical electron theory and the assumptions of quantum free electron theory. However, we have the expression for electrical conductivity in the case of metals given by the Dudd and Lorentz in the case of classical electron theory of metals. So the expression will be like this: sigma is equals to Ne square tau by Me, where sigma stands for electrical conductivity of the respective metal and N stands for the concentration of electron in the respective metal, E will be the charge of electron, tau will be the mean collision time, and Me will be the rest mass of the electron. This is the main equation which is given by the Dudd and Lorentz in order to explain the electrical conductivity of metals. Of course, it explains some part of the property of electrical conductivity, but it fails to account some of the quantum mechanical behavior which is related to the electrical conductivity of metals. That is, the first one is the failure which is identified in order to explain how the variation of electrical conductivity with respect to the temperature. The second failure is identified. So how the conductivity varies with respect to the material to material, and will the concentration of electron which can be varies with respect to the metals or not. How the electrical conductivity which will be varies with the concentration of electron, because it contains the term N. N means the concentration of electron. As per this particular equation, it is directly varies. Will it be experimentally proven or not? That we can see in the next slide. The first I will take the failure of classical electron theory. So the first failure is identified. So in the case of temperature dependence of electrical conductivity, how the variation of electrical conductivity with respect to the temperature. So the first is, as per the classical electron theory, main assumption I have already given in the previous video. The main assumption of classical electron theory is the each and every electron which is behaving like a free electron or whose behavior is similar to the behavior of gas molecules. So that means the electron which are going to be treated as a gas molecules. Hence the kinetic energy of electron, that is half mv square, we all know it is a kinetic energy of electron because whose behavior is similar to the behavior of gas molecules. Hence half mv square is equals to 3 by 2 kT. 3 by 2 kT is the kinetic energy of gas molecules. Half mv square is the kinetic energy of electrons. And because of the behavior of electron is similar to the behavior of gas molecules, hence whose kinetic energy is also equal to the kinetic energy of gas molecules. So in this particular equation, you can notice half mv square th. V square th stands for thermal velocity. Vth stands for thermal velocity of electron. 3 by 2 kT. K is the Boltzmann constant. T will be the respective temperature of the material where it exists. So here you can see that thermal velocity is directly proportional to the, that means thermal velocity is proportional to the temperature. How it will be proportional to? That means Vth is proportional to the root T. That means V will be square. In order to remove the square, we should have to take the square root. That is Vth is proportional to the, or Vth is equal to the square root T. And next is the mean collision time. The mean collision time is, you can treat this equation as 1, and mean collision time tau is equals to 1 by Vth. As the thermal velocity increases, then the correspondingly mean collision time is going to be decreases. So velocity is more, collision time is less. Velocity is less, collision time is more. So these two are the main equations. By using 1 and 2, equation 1 and 2, we can write the tau is equal to 1 by root T. So because Vth is equals to root T, tau is equals to 1 by Vth. In place of Vth, if you substitute root T, we will get a equation tau is equals to 1 by root t. You can call this is equation number 3. From the expression of electrical conductivity of metals, that expression is like this: sigma is equals to Ne square tau by m. So in this particular case, sigma is proportional to the tau. Tau means a mean collision time. So sigma is proportional to the tau. From this particular, from the equation number 3 and 5, we can directly write sigma is inversely proportional to the square root t. So because of this you can see that the sigma is inversely proportional to the square root of temperature. This will be the equation 6 will be obtained from the classical electron theory of metals. As per the Totten-Lorentz theory, sigma is inversely proportional to the square root of absolute temperature of the material. But if you consider the experimental identification, the sigma is inversely proportional to the temperature. But in the case of classical electron theory, it shows that sigma is inversely proportional to the square root of temperature. As per the experimental evidences shows that sigma is inversely proportional to the temperature. From 6, upon comparison of 6 and 7, so we can come to the conclusion. So there is no direct or complete explanation of electrical conductivity of metals in the case of classical electron theory of metals. Hence, which confirm that temperature dependence of electrical conductivity is not sufficiently explained by the classical electron theory. This will be the one of the main failure of classical electron theory. Of course, it can explain rest of the part of characteristics of metals, but it can find the failure while explaining the temperature dependence of electrical conductivity. Next is another failure which is also identified in the case of metals, that is in the case of dependence of electrical conductivity in metals on electron concentration. How the concentration of electron can vary the electrical conductivity. So you can consider the metals like copper and aluminium. Copper and aluminium, they are different by their concentration of electrons. They are different. So if the concentration of electron, which can vary as per this particular equation, sigma is proportional to the n. That means as the concentration of electron increases, then correspondingly the conduction ability of the material, called as conductivity, can also be increases. So this will be the relation which gives the conclusion. But if you consider the metals copper and aluminium, the copper electron concentration in the copper is less than compared to the aluminium. Copper is monovalent and aluminium is divalent element. So as per the experimental evidences, so copper have more conductivity than compared to aluminium, even though it has less number of electrons in the outermost shell, and total number of electrons are also less than compared to the aluminium. So how, if as per this theory, if the sigma is proportional to n, then aluminium should have more conductivity than copper. But in experimentally, this kind of property is not noticed in the case of copper. Copper having the more electrical conductivity than compared to aluminium. So because of that, so not only we cannot supposed to be say it is only depends upon the concentration of electron. The rest of the parameter also plays an important role in the case of classical electron, in the case of conductivity of metals. Hence, this is one of the failure of classical electron theory. So this is our conclusion. So the concentration of electron in the case of metals, how it will be varies its electrical conductivity, that is not sufficiently explained by the classical free electron theory. So this will be the second failure. So in order to overcome these failures, Sommerfeld have attempted to frame the new kind of a theory called as quantum free electron theory. So this has some certain sort of assumptions. By using the certain assumptions, the Sommerfeld have given the theory. It sufficiently explains all the failures of classical free electron theory. So where the classical free electron theory fails, in that place the Sommerfeld have successfully explained the characteristic property of metals. So hence universally this quantum free electron theory is nowadays it is an accepted theory to discuss the electrical conductivity of metals. So what are the assumptions? So we will look up one by one. The first assumptions of quantum free electron theory. The first assumption, which is quite different than compared to classical free electron theory. What is, in which part it is quite different? So you can look up, the energy of free electron is quantized in terms of energy states. But in the case of classical free electron theory, so they are simply consider the electron as a gas molecules. So all the gas molecules are having the energy, that is 3 by 2 kT, that will be equals to half mv square. So they are going to take an average energy half mv square or 3 by 2 kT. But in the case of quantum free electron theory, the energy of electrons is quantized in terms of energy state. Each and every electrons exist in the part of electrical conduction. Their energy becomes quantized, unique energy they may have. Quantization means discrete sets of energy. Each and every electrons, they are different in terms of their energies. Next is, the energy states are available. So the distribution of electrons in the various available energy states, it obeys Pauli's exclusion principle. So how the electron which is going to distribute themselves among the available energy state, that must be obeys the Pauli's exclusion principle. So the third and fourth assumption is common in case of classical free electron theory also. The first two assumptions are different from classical free electron theory. What are the first two assumptions? The free electron energy is quantized and the distribution of electrons in the various available energy states obeys the Pauli's exclusion principle. The third assumption is electron can experience the field by positive ion core is constant. Each and every electron, they experience the constant positive ion core field, and the interaction between the two electrons are going to be neglected because they are not supposed to be taken place, because the electrons are negative carriers. The two similar carriers cannot going to interact with themselves each other. So these are the main four assumptions. Based on this assumption, Sommerfeld have successfully given the quantum free electron theory of metals. So we will look up in detail one by one what are the rest part of the quantum free electron theory upon discussion of assumptions of quantum free electron theory. So next is the density of energy states. In order to discuss the density of energy states, I have already quoted in the discussion of assumptions, the energy of each electron is quantized in terms of energy states. So energy states, how the distribution of electrons in the various available energy states obeys the Pauli's exclusion principle. Then how many number of energy states are going to be exist, that term is, the answer for that term is given by the density of energy states. In order to understand the density of energy states, first I will consider a isolated atom that exists in the gaseous state. Their energy states will be like this. The lines are representing E1 and E2 are called as energy levels for the case of isolated atoms. So when it is exist in the gaseous state, because so the atom cannot be disturbed in the isolated state or in the gaseous state, which is not affected by the nearby atom because the distance is too large. So hence the energy states of atom in the isolated state called as energy levels. Even it comes to the case of liquid state. So in the case of liquid state, the atoms are much closer, hence their energy states are going to be appear closer and closer. So this will be continuous. So you can see initially in the isolated state we can see the discrete sets, but they are having the spacing more. But in the case of liquid state, the atoms comes closer. Because of that, the atoms the spacing of energy states are going to be reduced. So next, for the case of solid state. In the case of solid state, each and every atoms are arranged in the closed manner, and each and every atoms are bonded with nearby atoms. The energy states of each and every atoms are discrete sets, but whenever it is exist in the bonded form, so each and every atoms are having the same type of energy states, and then they are arranged closer and closer, hence their energy states are going to overlap with each other. Because of the overlapping of energy states of each and every atoms, we can't distinguish where the energy levels are exist. We can get the region of energy states, hence it appears like a band like structure. Band is nothing but consists of many number of filaments of energy states. So there are n number of energy states. You can see that this is the band. The whole region will be called as band. The bands are having the energy states. The energy states are arranged in the closely compactly compact arrangement. If you take macroscopic view, it is appears like a single line. If you take microscopic view, it is appears like a many number of lines. So the region of energy states where it lies, that particular region called as energy bands. So the energy bands normally comes in the case of solids. So the metals are belonging to solids, hence we need to understand how many number of energy states are available within the energy band. So you can see in the isolated atom only one energy levels are exist. You can't possible to discuss the density of energy states because their existence of one. So here also a few number of energy states that also be found out by counting. But in the case of metals, there are n number of atoms are arranged. Each n number of atoms are having the n number of energy states. All those together they can form the band like structure which consists of many number of energy states. Hence the necessary to discuss how many number of energy states are available in the energy band, because in order to accommodate the electrons as per the Pauli's exclusion principle. The first is density of energy states. The density of energy state is having the simple definition. In the case of solids, the energy levels of free electrons are regarding the energy bands. They can be considered as energy bands. So for the isolated atom, energy levels. The energy bands. In each energy bands, there are countless number of allowed energy levels are exist. You can see in the figure first, there are countless number of energy states are available in each and every bands. These energy states are arranged as like a quasi-continuous. Quasi-continuous means if you take a macroscopic view, it will appear like a single shaded band. If you look into the microscopic view, it will appear like a discrete lines. So this is the type of arrangement called quasi-continuous. So next is I will consider the same band with another figure. So E1 is the bottom of the band and E2 will be the top of the band. So this is the bottom of the band will be E1 and top of the band will be E2. So in between E1 and E2 there are countless number of energy states are available. In order to give the definition for density of energy states, I shall consider a small elemental energy range called as dE. dE is the elemental range between E1 and E2. So the density of energy states is symbolized by the factor called G of E. G of E stands for factor of density of energy states. It is defined as the number of energy levels are available per unit volume per unit energy range centered at E to E plus dE. The number of energy states per unit volume between the energy levels E and E plus dE is denoted as density of energy states. Density of energy states is nothing but number of energy states per unit energy range per unit volume. So it is symbolized by G of E. So G of E factor will be varies. I have given the equation G of E is equals to 8 root 2 pi m to the power of 3 by 2 by h cube into e to the power of 1 by 2 into dE. You can see that all the factors in the right hand side, they are going to be constant except energy. So the energy, if you consider the energy which is closer to the E1, by the time G of E is different. If you consider the energy which is closer to the E2, by the time G of E will be varies from bottom of the band to the top of the band. That means E1 to E2. The G of E is going to varies with respect to the energy range. So the variation of energy state, how it will varies with respect to the energy, you can see in the next slide. So if you plot G of E by choosing along the y-axis and energy along the x-axis, so how the variation of G of E with respect to the energy, if you can move from bottom of the band E1 to top of the band E2, how it will be varies. Initially it will be varies too fast, then upon that it will be varies slowly. Because of that we will get a variation like this. This is the kind of variation you may get for the variation of energy state from the bottom of the band to the top of the conduction band. The variation of energy state with respect to the energy as shown in the above figure. Therefore G of E is mathematically a continuous function. You can't find any discreteness. So in the case of isolated atom, you can't express a continuity in the E1 and E2, but in the case of energy band we can find a continuity, some more continuity, because they are arranged closer. So hence mathematically G of E becomes continuous. So next is the Fermi energy. The Fermi energy is another factor which may require. So because based on this Fermi energy, it is we can get the idea about how the electrical conductivity which will be varies with respect to the metal. The Fermi energy is having the simple definition. It will be like this: the energy corresponds to the highest occupied level of electron at absolute 0 Kelvin. This is known as Fermi energy. Fermi energy is the energy of highest occupied level of electron at absolute 0 Kelvin. So let us consider the energy states. You can see in this particular case the energy states are available in which we should accommodate the electrons by using the Pauli's exclusion principle. So let us assume the copper is an element which has 23 electrons. Because of 23 electrons, so there are n number of energy states are available here. So we can't accommodate all the 23 electron to all the available energy states. We should have to go with certain particular procedure. So as per the Pauli's exclusion principle, lower energy electron will be filled up in the lower energy state, but those two electrons are different from each other. They are having the opposite spin and momenta. Such electrons which are going to be accommodated. So likewise we will accommodate the available electrons in the among the energy states one by one. We can reach to the maximum numbers because the availability of electron is only 23, but the availability of energy states is n number of energy states are available. So because of that we can't possible to accommodate from some energy states onwards. So where it actually the maximum occupied, this is the maximum occupied energy state, this is the final electron which is coming to the last level of occupation of energy states. So the energy corresponds to this particular electron. This is the highest occupied level. The energy corresponds to the highest occupied level of electron at absolute 0 Kelvin. The rest of the electrons which are not considered, because those electrons will be remained in the same atom, but the final electron is called as valence electron, that can move from one atom to another atom. Because of that, whose energy is important, because the transportation electron is this one is the transportation electron. Because of that we should concentrate on the energy of this particular electron. So I have already quoted in the previous video, the electrons in the atoms, that means free electrons in the atoms, act like a carriers for the transportation of electrical energy from one point to another point through the metal. Hence, if it is acts like a carrier whose energy is important, if the carrier is having the less energy, the carrying ability is less. If the carrier is having the more energy, then the carrier can carry the more order of energy. That's why we shall focus on the energy of highest occupied. This is called as active electron. Active electron, it can having a permission to move from one atom to another atom in anywhere in the metals. So this occupation diagram will be different for different metals, because some metals are having the 23 electron, some are having the 24, 25, like that. So depending upon the number of electrons, the Fermi energy varies from material to material. So at absolute 0 Kelvin, the electrons are occupying within the permitted energy levels by the Pauli's exclusion principle. These are the electrons which are occupied by the Pauli's exclusion principle. As shown in the figure, up to the particular energy state, the electrons are filled, and above which the energy states are vacant. Next is, so the Fermi energy of a metal is given by the expression, that is EF stands for Fermi energy, which is equals to h square by 8m into 3 by pi whole to the power of 2 by 3 into n to the power of 2 by 3. Here also the concentration of electron is a main criteria. The rest of the terms in the RHS are constant except n. N varies and their Fermi energy is also varies. Hence the Fermi energy is different for different metals. Next is the Fermi factor. The Fermi factor is the factor that is going to decide the probability of occupation of energy states. So the occupancy of energy levels alters continuously by the thermal excitation process. So that means if you supply the temperature, these electron may get the energy and upon receiving the energy can jump from one energy state to the another state. So because of the temperature, that can alter its probability of occupancy. Before the application of temperature, you can see that the occupation is complete occupation below the Fermi levels. Whenever if you apply the temperature, given the temperature, then these number of electrons can jump from lower energy state to the higher energy state and remain the energy state below the Fermi level as empty. So how the variation of probability with respect to the temperature, that is accounted by the Fermi factor. So hence the probability of occupation of each and every energy state changes with respect to the temperature. The Fermi factor is the probability of occupation of given energy state in the material at thermal equilibrium. It is simply called as Fermi factor. Simply describe the probability occupancy variation with respect to the temperature. So how it will be varies, we can calculate mathematically by this equation, that is f of E stands for Fermi factor, which is equals to 1 over e to the power of exponential e to the power of E minus EF divided by kT plus 1. This will be the equation for Fermi factor. Next, in the next video, we will discuss temperature dependence of variation of Fermi factor. Thank you very much. I hope it will be useful for you people, and please read the notes. If you have any kind of doubts, you can text me through message. Thank you very much.